How's everyone feeling today? Glad to hear. Well, this is the last week of class. Exams are in 1 week, and we got one more short day of things that I want to talk about. Just to cover the aspects of electricity that I think everyone should be aware of. It's rain is not raining on Monday. At least the Wi-Fi. So, one more day of learning. Wednesday we will cover all the stuff that you need to know for the exam. Any questions, needs, concerns, etc. before we get started? All right. This will be the last new information that we cover. There is a homework assignment on Brightspace so that you can practice it, and there might be one question out of about 20 or so on the exam that covers very briefly these topics. Electricity. Now, who can describe what electricity physically is? Okay, and what is a lightning bolt physically? What is a lightning bolt made of? Electrons. Very good. Electricity is just the motion of electrons. Electrons being one of the 3 subatomic particles that everything that is made of matter is made of. And we consider electricity to be the motion of electrons because they're the particle that's most easily able to move. Protons and neutrons live in the nucleus of an atom, and they're kind of stuck. They don't really get to freely do much of anything. Electrons, since they orbit the electron the atom body, are able to actually leave the atom, and therefore they are actually able to go from point A to point B. They are able to all surge in one direction, traveling like the current of a river, and that's what the electricity physically is. Electrons literally zapping and zipping from point A to point B all together at the same time in the same direction. So to get electricity, you have to have a bunch of electrons at point A and then all at once rip them all towards point B. And that's basically what a lightning bolt is. The oldest form of electricity that humans were aware of. My art's not great, but that's a cloud and that's a tree. Technically, that's the intent anyway. And the way that lightning works is, when you have a bunch of clouds in the sky, they all rush past one another and they charge each other up via friction. You may be familiar at this point that friction can build up static charge, especially if the humidity is low and you're wearing wool socks. Sound familiar? Clouds charge up a bunch of electrons via friction. When you electrically charge yourself, you're just kind of gaining more electrons than you are supposed to have. Normally you're supposed to have the same amount of electrons as protons, but if you increase the number of electrons without changing the number of protons, you end up net negatively charged. And if you have a bunch of extra negative charges in your body, they don't really want to hang out near each other because like charges repel. So the cloud generates just a metric ton of extra electrons that don't want to be anywhere near each other. And all they're doing is waiting for one opportune moment when the cloud gets just barely close enough to this tree and the positive charge is in the tree, that there's enough force to literally rip all those electrons out of the sky all at the same time in the form of a lightning bolt. Now, can you see electrons? No, I can't at least. So there are electrons passing from the cloud into the tree and then through the tree into the ground. But what are you actually seeing in the lightning bolt? Kind of, yes. When electricity passes through something, because electrons always need something to travel through, they're not really good at just passing through empty space. When electrons travel, they tend to physically jump to the next atom and then jump to the next one, just kind of constantly daisy chaining what atom they're currently orbiting. So they need atoms to orbit. And so what's happening is the electrons are just continuously jumping through the air molecules. And when electrons do that, when they jump from atom to atom, they tend to leave energy behind, usually in the form of heat. So what you're actually seeing here is superheated air. You know how during a lightning storm, or if there's just a bunch of electricity nearby, sometimes you can kind of smell something different about the air. I sometimes can smell when there's a thunderstorm coming, and if I get too close to like an old TV, there's this weird staticky ionized smell sometimes. That is literally heated charged air. The smell of heated electrically charged air, which is basically plasma. So what you actually see for any electricity, it doesn't have to be a lightning bolt. If you see any electric spark, what you're seeing is, for the briefest moment, plasma, as electrons surge through the air and leave a bunch of energy behind, temporarily superheating it into plasma, and plasma tends to glow. So you don't actually see the electrons. The electricity is made of electrons. What you're seeing is the glow from the plasma that the electricity temporarily leaves behind. Does all that make sense? Okay. Now that's usually why you can only see the electricity when it passes through air. When electricity is passing through a metal wire, you don't really see it because it's not passing through air, it's not turning anything into something that glows temporarily. So electricity through a metal wire, you can't really tell that it's there, and that's kind of why charged metal wires are dangerous. You don't really know that they're charged until it's too late. But humans have taken advantage of this, and we figured out that if you run electric current through gas, you can make it glow, and that's all modern light bulbs are. There's just gas in a tube that they are running electric current through. So there's plasma above you right now, and that's what the sun is made of. So electricity is just moving electrons. The amount of electricity depends on how many electrons are moving. If you want a big lightning bolt strike, you've got to move a bunch of electrons all at the same time. We measure all of this. We measure electricity in general using three main variables, which we will be describing today and in lab this week. You can kind of consider all of today just the information you need for lab this week. The formula that's on screen, and it is the same formula twice, just rearranged. We call this formula Ohm's law. That name is pronounced Ohm, O-H-M. And the three variables in that formula are the three things that scientists measure that relate to how electricity is going to travel through something. How much electricity you have, how much can travel through a specific system. I'm going to look at this particular formula here, just the way that it's written here. Big V equals I times R. Technically delta big V equals I times R. Note that that is an uppercase V, not the same lowercase v that we've been using for velocity this entire time. Although I suppose we also use capital V for volume. Physics ran out of letters a long time ago. These three variables, first is electric current, and that is I for reasons that have not adequately been explained to me. The I in these two formulas stands for electric current. And the measurement of electric current tells you how much electricity you have moving through a system. The electric current is a lot like the current of water. If you have a lot of water current, you physically have a lot of water molecules moving through a specific area. If you have a lot of electric current, you have a lot of electrons moving through a specific area. So more electricity means higher current. Next thing we're going to talk about is voltage. I'm going to make water analogies a lot because electricity does kind of flow very similarly to water. Voltage is the electrical equivalent of water pressure. Voltage is what makes current flow, like how water pressure is what makes water flow. And the last thing we're going to discuss is electrical resistance, how difficult it is for electricity to flow through a specific object or place. So those are the three main things we're going to be talking about today and in lab this week. Questions so far? All right. First up, we'll go a little bit more into the notion of electric current. Again, if you see an uppercase I in the Ohm's law formula, V equals IR, the I is the current measurement, the measurement of electric current. And again, current tells you how much electricity you've got passing through something. The bigger the current measurement, the more electrons are passing through that particular thing every second. You're not really going to need this formula for anything. I just have it here to kind of demonstrate. The measurement of current is the amount of charge passing per time. Charge in this case meaning electrons. The more electrons pass through something, the more current you have. And that means if you are being, heaven forbid, electrocuted, the more current you're being electrocuted with, physically more electrons are going to surge through your body. And that's why current is dangerous. It is for this reason that most human-built electrical devices use as small amounts of current as possible, because current is the part of electricity that is dangerous. Current is the electricity itself, and it represents how much electrons, how much energy is going to pass through something. We measure electricity in units of amperes, which is most commonly abbreviated to amps. Have you heard of amps before? So amps represents, again, the amount of electricity. And 1 amp will kill you dead. 1 amp is already a ton of electrons passing through you every single second. 1 amp will kill you, if not immediately, within a second or two of 1 amp passing through your brain and or your heart. So 1 amp is more electricity than most machines you will deal with regularly uses. For safety's sake, most devices scale down to about a milliamp of current required. They're designed to use literally 1,000 times less than an amp so that there's no danger of zapping yourself. So just for scale, most appliances and devices you own should have about a milliamp, maybe 10 milliamps running through them in any given moment. You only get up near amps when you're going into like high power output industrial devices surrounded by a bunch of safety equipment and labels. But amps are the dangerous part of current. Does that make sense? Dangerous part of electricity. All right. Next thing that causes electricity that we measure is called voltage. This is hopefully another term that you've heard of before. Voltage isn't the same as the amount of electricity. Current is the amount of electricity. Voltage is basically the pressure that causes electricity. Current is the amount of electrons that are moving over time, and voltage is the force, the pressure that causes them to move in the first place. I compared it to water pressure a second ago. If you want water to flow from point A to point B, you have to exert force and pressure on that water to get it to flow away from point A and towards point B. voltage does the same thing to electricity. In the case of a lightning bolt in a cloud, when there's a bunch of electrons all grouped together in the cloud, there's a very high voltage in that cloud that wants to push the electrons away because the electrons don't want to be anywhere near each other. Negative repels negative. Instead, down here in this tree where there's a bunch of positive charges, this is a very low voltage. And like water likes to flow from high pressure to low pressure, or high elevation to low elevation, electricity wants to flow from high voltage to low voltage. So the voltage in this case represents the high amount of electric potential charge built up here that doesn't want to be anywhere near each other. And there's a lot of voltage, a lot of force that's going to push it towards the tree through the air. Voltage is the force that drives electric current to flow. And so to make electricity happen, you need voltage. And that's why most, well, literally every electrical device needs some sort of a voltage source. That's what batteries are. Or just the wall outlet. You need some source of voltage to get electricity moving, because there's already electrons everywhere. Your body's filled with electrons. To get those electrons moving, you require voltage to do so, and that is why batteries and wall outlets are used. That supplies voltage to the circuit to get the electrons within the circuit flowing. So I will occasionally refer to batteries as voltage source, because the voltage is what you need to get the current going. The current is then what delivers the energy to whatever you've got it flowing through. Questions so far? I want to bring up the difference between current and voltage. Voltage doesn't necessarily hurt you. High voltage amounts do not inherently mean danger. If you see a sign that says warning 10,000 volts, it could be dangerous, but the volts aren't what kill you. High current kills you. So if you see a sign that says 10,000 amps, avoid it like the plague. 10,000 volts just means the potential for high amounts of current. So it would really only be dangerous if you are physically touching it. But high current, that means electrons are flowing already everywhere, and you should avoid that very strongly. So current kills you, voltage just has the potential to kill you. Current will kill you. Voltage might kill you if it causes high current. And we measure voltage in volts. It's about one of the only units that makes any sense. So, voltage pushes electric current. Current is the electricity. There's one last ingredient you need when examining an electric circuit or just the flow of electric current. And that is you have to acknowledge the resistance of what you're trying to make the electricity flow through. Are you familiar with the notion of an electrical insulator or resistor? The idea that electricity just doesn't want to flow through certain things, like how we coat most of our wires in rubber or plastic. Different materials just have different electrical resistances, which is to say if something has a high resistance, it's very hard to force electricity through it. Certain materials just inherently prevent electrons from passing through them very quickly. Rubber being probably the most common high resistance object that humans deal with on a regular basis. Meanwhile, if something has a very low resistance, it's very easy for electricity to flow through it. This tends to be things like metal wires and occasionally water, which is why you don't go swimming in a lightning storm. And the resistance of something does affect how a circuit with that element in it will work. If you build a circuit, you want to build a circuit, if you want to get electricity to flow through something, you need three main things represented in this Ohm's law formula that I've been motioning to for a while. Those three things being voltage, usually provided by a battery, because that is the pressure that will make electric current flow. You need a closed connection for that current to flow through. These are the wires. And they all have to be connected. You need a solid, uninterrupted path from one end of the battery all the way back around to the other. If you break one of these wires, the current stops flowing. So you need a battery, voltage source. You need an uninterrupted wire from one end of the battery to the other for current to flow. And you need whatever it is you're trying to get that current to flow through. That is the wires, but also like a device that you are trying to power with the electricity. Anything that you run electricity through acts as a resistor. So this symbol right here, this squiggly line, it's just the symbol that electricians use for resistors. And that can be anything. That could be washing machine, cell phone charging brick, you if you're touching the wires, so don't do that. This is just whatever you are trying to run current through. And it's going to act as a resistor because everything resists electricity flowing through it to some degree. If it has very low resistance, it's easy to push electricity through it. If it has high resistance, it's difficult to push electricity through it. But everything counts as a resistor because everything has some resistance. I've measured my own resistance. It's very high, which is good because you don't want electricity flowing through you most of the time. The amount of resistance that you are trying to push the current through affects the rate at which the current gets pushed through it. So if you need high amounts of current in your circuit, you would want to build it with a very small resistor. But if you don't need high amounts of current, you could use a higher resistance resistor. And something's resistance can also be thought of as how much energy it takes away from the electric current. Because when you run electrons through something, they leave energy behind. And this is why being electrocuted can hurt you. If there's electrons passing through your body, they're leaving energy behind in the form of heat. And so if you're getting electrocuted, you're basically being roasted from the inside out. The higher your resistance, the harder it is to push electrons through you, but it also means that you are leaching more energy out of those electrons, which again is the dangerous part of being shocked. You don't want a bunch of energy coursing into your body. But these three things combined, current, voltage, and resistance, are the things that determine how a circuit's going to work. They're the three things you need in order to build a circuit. Bless you again. And they work together to create this equation here called Ohm's law. We call it Ohm's law because resistance is measured in a unit called, can I write that down? Oh. Resistance is measured in a unit called ohms, named after a scientist. So it's the name Ohm's law is the name of this formula, and resistance is measured in units of ohms. So when you're building circuits, you need these three things, and how they all interact together in this formula will determine how well the circuit works. If you need high amounts of current, you're going to need a lot of voltage to push the current through whatever resistor you're using. And devices count as resistors. When you plug anything into the circuit of your house, what you're doing is you are adding an extra resistor into the chain. So you're just adding an extra thing that the electricity has to pass through on its way around the room. How's all this feel? All right. Quick question. We are setting up a lab, basically building a circuit. We're doing the wiring in a room to make sure that electricity flows through the room at a specific rate. In order for our devices to get the power they need, they are going to require 2.5 amps of current. So that tells us how much electrons need to be passing through our equipment every second for them to have power, the power they need to be functional. We have access to a 100-volt battery, which is a lot. That's like car battery size. In order for, my very quick question for you guys, in order for that 100-volt battery to be outputting 2.5 amps of current, how much electrical resistance can our system have? Can the cables and the machines themselves have? What is the maximum resistance of our circuit allowed to be so that this 100-volt battery is outputting 2.5 amps of current?
Ready?
40, precisely. We've got 100 volts, that's V, 2.5 amps, that's I, V equals IR, therefore 100 equals 2.5 times R. That R is going to be the needed resistance of our system so that the 100 volts is pushing 2.5 amps through it. Basically, the resistance of your entire circuit kind of acts as the speed limiter for the current. If you have a small amount of resistance, your voltage will push more current through, but if you've got a large amount of resistance, the same voltage will be pushing out less current because it just can't flow as fast through a higher resistance circuit. And you add on to the resistance of your circuit by adding anything into it. Any device cranks up the resistance of your circuit. In this case, what we're doing is calculating the maximum amount of resistance that we can have in this situation to make sure we're getting that 2.5 amps. So we divide by 2.5 and we do get the 40 ohms as said. The symbol for ohms is Greek letter omega, by the way. So when you see the horseshoe in lab today, that's what it's referring to. And that is your introduction into electrician math. How's it feel? All right. Really quickly, before moving on, of the three numbers from this example, the 100 volts, the 2.5 amps, and the 40 ohm resistance, which of those three numbers is the most dangerous? The amps. Very good. 2.5 amps will probably kill you in less than a second. So this is a very dangerous laboratory if you are an electrician. I'll also point out, this is not a lot of resistance. Most resistors are like 1,000, 10,000, 100,000 amps. This is a very small amount of electrical resistance. So there's really nothing preventing the current from flowing very fast. That is something we'll be exploring in lab this week. The resistance is important because if you want a lot of current to flow, you need very low resistance. If you want to stop current from flowing, you need high resistance. This is important again for talking about insulating your wires, because electricity is very lazy. It's not going to want to flow through something high resistance if it has the option of flowing through something low resistance. That is why, rubber cabling works, why coating the wires in rubber stops you from getting zapped. There can actively be electricity flowing through this wire, and as long as it's coated in rubber, I can touch it and be fine, because electricity always chooses the path of least resistance. So these metal wires have a very small amount of resistance, as we just calculated, meaning that the electricity wants to flow through that. If we coat the wire in rubber having a resistance of hundreds of thousands of ohms most of the time, because it's not easy for current to flow through that, even if I am touching the rubber cable that the wire is encased in, the electricity is not really going to want to jump out of the wire through the rubber and through me, because it would have to jump through 100,000 ohm rubber cabling in order to do that. If the electricity has a choice of flowing between easy 40 ohms versus 100,000 ohms, it's going to choose the 40 ohms, because electricity follows the path of least resistance. And that's why you're able to coat them in rubber and not get shocked even when you're touching them. Does that make sense? As long as you're not touching the metal part. Related tip about this, if you ever know that you're going to get shocked, like if you know lightning is about to strike you somehow, electricity follows the path of least resistance, and you can use that to avoid dying if you somehow know you're about to get electrocuted. Basically, the two parts of you that you don't want current to flow through are your brain and your heart, because those are the two most important organs to keeping you immediately alive. So to make sure that the path of least resistance doesn't involve any of those, you want to make sure the current enters this hand and exits your right foot. So if you cannot avoid getting electrocuted, make sure the lightning hits this hand, and this is the only foot touching the ground, so that the path of least resistance from high to low is hand to foot, and that avoids these two parts of you. Never have current enter one arm and exit the other, because that'll carry it straight through your heart. Always right hand or right foot, because your heart is technically a little on the left. Now, your best option is just be nowhere near the lightning. This is like last case. This is emergency scenario. Is that clear? Okay. There's one more thing I want to talk about related to electricity. I consider all this background information to this last part, because this last part is how you calculate your electrical bills, which I think for most humans is the thing they care most about when talking about electricity. Your electric bills depend on the related principle of power. And we've actually talked about power before. If you remember from several chapters ago, power was the rate at which work is performed, the rate at which energy is used. And we would measure it in watts, right? I brought up then that you may have heard of watts in an electrical context. Same watts. Same power, technically. Power is still the rate at which energy is used. And the power requirement of your home affects what your electricity bill is going to end up being. For example, a 60-watt light bulb, since power is energy used per time, 1 watt is 1 joule used up every second. Therefore, a 60-watt light bulb needs 1 joule of energy. Sorry, a 60-watt light bulb needs 60 joules of energy every single second from the electric current in order to stay lit. If it's getting less than 60 watts, less than 60 joules every single second, it's going to get dim and eventually go out. So the wattage of your appliances directly correlates to how much energy they need, and therefore directly correlates to how much they cost you to keep running. Lower wattage appliances cost less because they need less energy per time. And what the electric company is billing you for is energy. Not necessarily current, but the energy carried in that current. So first tip, when you get to the point where you are having to deal with electrical bills, lower wattage, better, for your bills at least. Thankfully 60 watt bulbs usually are the older type. Most bulbs you'll buy these days are probably about 20 to 30 watts, so that's already a little bit better. But still, in general, lower wattage, lower electrical costs, pardon me. Now the way to determine the wattage of something, there's a couple related formulas here for electrical power. Power is still capital P, and power is still work over time. That's still true, that didn't change. These are extra formulas for the electrical version of power. The power a device needs is equal to its current requirement times its voltage requirement. Current tells you again how much electrons need to pass through it every second. Voltage tells you how much electrical pressure is needed to push that current through it. If you know the requirements of a device, these two requirements, you can figure out its power rating. And there's a couple other versions of the formula. This is just combining in Ohm's law to substitute around things you know or things you don't know. Since power is I times V squared, not V squared, just voltage. Voltage is equal to current times resistance. That means you can plug in current times resistance instead of voltage. It's already times I. So this here, I squared times R, is the same, just with Ohm's law substituting the voltage. So these extra bits here, they're useful based on what you happen to know. If you don't know current, but you do know voltage and resistance, you use this version, so on and so forth. Bless you. As long as you know two of these three things about your circuit, you can figure out the power requirement of the circuit, and then you can figure out how much it is going to bill you at the end of the month to keep it on. Is that good so far? All right. So, first question. Going back to this sample question, the 100 volt battery, 2.5 amps of current, and 40 volt resistance. What is the wattage, the power requirement of this setup? Yes, 250. P equals IV, therefore P is 2.5 amps times 100 volts. That is 250 watts for this laboratory. That is the wattage of the laboratory, and that again tells you the joules per second needed to keep your equipment active. Now as wattages go, that's not actually that bad. That's probably the wattage of 2 laptops. Don't know why the current level is that high. But now I'm going to show you how to use that to calculate electrical bills. So, different question. You leave on a 60 watt light bulb for 7 hours a night. Now, 60 watts again means 60 joules every single second, and the joules is what you're getting billed for. Unfortunately though, the power companies in America don't really use units of joules for the energy that you're using. They use a different unit called kilowatt hours. If you've ever looked at an electrical bill, you might have seen this before. This is a new unit called kilowatt hours. I'm going to spell that out. And this unit is literally the wattage of your device times the hours it is turned on. It's not kilowatts over hours, it's kilowatts times hours. So that's why it's a hyphen and not the division sign. So the amount of kilowatt hours of energy that something uses is its wattage in kilowatts times the hours that it is turned on. So in the case of this light bulb, 60-watt bulb on for 7 hours, we're going to take its wattage, convert it from 60 watts to 0.06 kilowatts. We multiply that, and I'll write in the units. So this is the bulb, this is its wattage in kilowatts. We're going to multiply that by 7 hours, and that will tell us the energy that the bulb uses in units of kilowatt hours, which is the unit that U.S. electric companies use to bill you for. .06 times 7. So this light bulb turned on for 7 hours a night will run you 0.42 kilowatt hours of energy used per night. This is a unit of energy. So it tells you the same thing as joules, it's just a different unit. We could convert this to joules if we wanted to, but power companies don't use joules, they use this. Now, if you ever looked at an electrical bill, you would see the amount of kilowatt hours that your home uses, and you would also see how much you're being charged per kilowatt hour. Every unit, every electrical company has a going rate of cents per kilowatt hour. And how much that is just depends on where you live. South Carolina average is actually about 12.9 cents per kilowatt hour, so not much higher than this. Once you are aware of this rate, as the example, 10 cents per kilowatt hour, you can take the kilowatt hours of energy that you use, multiply it by the going rate, and figure out how many cents that device costs you per day. So we've got .42 kilowatt hours. I'm going to use this like a conversion to convert kilowatt hours into cents. 1 kilowatt hour costs 10 cents. And therefore, leaving on this light bulb for 7 hours a night costs 4.2 cents per night. So that's how much one light bulb would cost you in that scenario. You can do this for anything, any device, as long as you know its wattage, which is usually printed somewhere in its technical information or its instructions. If you know how many hours a day you have it plugged in and on, and if you know cents per kilowatt hour for your area. Again, South Carolina, the going rate these days is, I'll round it to 13 cents per hour. So, it might be about 5 cents these days for this light bulb, but that's for a 60 watt. Most bulbs you get these days are about 20 to 30 watts. So like 2 cents, 2.5 cents to have a light bulb on just for the dark hours. But that is per day. Multiply that per 30 for a month. But you can do this for any device as long as you know that information about it. Wattage, hours on, and cents per kilowatt hour from your electrical company. So, when you get to the point where you're paying electrical bills, my hope is that you can use this to help you make sense of the information and maybe figure out how to cut costs. Sound good? All right. Well, that's everything for today. And I got through all the electricity stuff that I wanted to. So, moving forward, bring these notes to lab this week. Lab will have you building circuits and doing some things with circuits, namely looking at the two main types of circuits. If you've done work with circuits before, those are series and parallel. So bring these notes to lab. Wednesday, we'll wrap everything up, make sure everyone's feeling confident for the exam. And please have a wonderful day. I did. Would you like your test? Yes. Go get the file in my office. You can, I can give the copy to you, and you can keep it to study from if you want. Yes, I'm just gonna need everyone's last Huh? That is your test tube.
What? I did.
Your test tube is there. Last name? Howard.
So,
Sorry.
you're good. About the lab that you said you look for it? Or
Oh, yeah,
If not,
I-
even if you can look for it, don't worry.
Yeah, I didn't get a chance to run through the stack yet.
Okay, no, that's fine.
Try your last name again.
Douglas?
Yes,
Cool.
yes.
But, I swear that one, it is done, we did do it.
I trust you.
Yeah, okay.
I'm just gonna go look through the file for the sake of my data brain.
Yeah, no worries. Alright, we'll be in that lab.
Alrighty.
See you later, thank you.
I have a question.
Yes.
Just because this is probably on the syllabus, I'm just being lazy, not even lying. How much is the final birth?
25%.
Okay. Compared to what's the tests?
Each
Test and.
Each test is also 25%,
Okay.
basically.
Also, I have a question.
Yes.
I did not come to class Friday. Did you give the test back?
I did.
Yes.